Yes, class. Good evening.
Good evening, ma'am. How are you?
I'm good. Okay, so who all have joined? Afra Ansar. Afra, right?
Yes, ma'am. Good evening.
Okay, good evening. Afra. Khalid, Memuna Salman, you all are there. Sana is there. Okay. So Afra's first class is it. Okay, Afra, currently we are studying wave optics. We are almost towards the end of it. Interference we have completed. We are just on the theoretical part. Theoretical part we have completed. Numericals of interference we have to do that. You can study along. Then see for diffraction, you can study diffraction in today's class. So some things it can happen that you'll not be able to understand. So let me know whatever things are there, because rest of the chapters have been completed in this batch. So after the completion, no, from here, whatever, from wherever you have joined, till the completion of semiconductors, as soon as it gets completed, I'll start again from chapter 1, the complete revision from it. So there you can join entire lessons, you can complete till again back to this topic, interference. All right. So have patience. Wherever you're not able to understand, let me know. What about your school syllabus? Is it completed?
Almost. We have last chapter left.
Last chapter left. All right. Okay, yes, class. So in the last class, we had completed with this intensity part. No, intensity distribution curve was over. So for bright fringe and dark fringe, we had obtained this kind of graph. So did you all revise this? Yes, Salman, Khalid, Memuna, you were there. Sana was there. Revised?
Yeah.
So after this, no, you will be having a test of wave optics. That's why I'm asking you. Okay, let's do a numerical then. Two numericals, let's do it. Let's complete with interference so that we can start with diffraction. See, for interference, no, this says that a beam of light consisting of two wavelengths. Two wavelengths are there. One is 800. Yes, Sana, you had left the class early. So this says that a beam of light consisting of two wavelengths, 800 nanometer and 600 nanometer. This is used to obtain interference fringe in YDSC on a screen that is placed 1.4 meters away. So 1.4 meters is what? Wavelengths are given for both the rays that are coming, both the waves that are coming from the slit. S1, S2 are the slits. Both the wavelengths are there, 800 nanometer and 600 nanometer. They are interfering, they are superimposing, all the phenomena of interference is occurring, and the screen is separated from the slit from the distance 1.4 meters. So 1.4, do you understand? Double slit and screen separation. This is capital D that we had used in the formula. If two slits are separated by 0.28 millimeters, 0.28 millimeter becomes what? This is what? This is your small d that we were referring in the formula. Remember, one capital V was there, one small d was there. So this is your capital D. This 0.28 is small d. You have to calculate the least distance from central bright fringe, where the bright fringe of the two waves coincide. So you do not have the number. See, rest of the things are given. Wavelength is provided, small d is given, capital D is given. But what about the number? Which fringe you will take? This is a problem, no? Here we do not know. Two wavelengths are given. Wavelengths are given. Yes, we agree with the fact that yes, one wavelength is given as 800 nanometer. Second wavelength is given as 600 nanometer. But which wavelength should I choose? 801, 601. And what is n over here? I cannot take myself randomly assuming that this is the first fringe. So see, for this, let's see, it is saying what? To obtain fringe in YDAC on a screen, play, just a second. So this says what? Beam of light consisting these two wavelengths is used to obtain interference on a screen that is placed this much distance. It is saying calculate the least distance from central bright fringe where bright fringe of the two wavelengths coincide. Both the wavelengths coincide. In the sense, see the diagram. It means this is the double slit that is given. S1, S2 are the slits. This separation is given as 0.28 millimeters. This separation is 1.4 meters. See, here is at central maximum, everything coincides. This we call as the central bright fringe. Right, this is the central maximum for which yn is 0. Let's take a point I have taken where for the blue one, blue is random, I have taken blue one. This is at yn distance, and for red one, this is ym distance. This is a particular point where both the wavelengths are coinciding. This point, class, this point where wavelengths are coinciding. Both the fringes are coinciding. Otherwise, it could have happened. No, blue is here, another blue is here, another blue is here. Then red are at separation and they cannot coincide. This is one single special point where they are coinciding. And if they are coinciding, it means yn will be equal to ym. It means both the separation will be equal. So if this is the case, how do we write the formula? And bright fringes are also given. What was the formula of linear separation from the bright fringe? N lambda capital D by small d was the formula. Put it. N lambda 1 capital D by small d. This is for yn is equal to M lambda 2 capital D by small d. Capital D, small d get cancelled. So small n becomes what? Lambda 2 by lambda 1 into m. Still, we do not have the value of either n or m so that we could calculate the values of n and m. Right? We do not have any one of it. No. So how can we calculate? I am equating, Sana, because see, this is a particular point. See over here. There are many fringes that have formed for blue one. There are many fringes that have formed for the red one. But this particular point where I have overlapped them, this is the special point where both are coinciding. Why I have taken the coinciding point? Because it is written in the question that calculate the least distance from central bright fringe where the bright fringe of two wavelengths coincide. Let's say this is that unique point where they coincide. It means if they are coinciding, so this length and the length for the blue one, both will be the same. Understood? Okay. Okay. So now see a technique to find this is, write it. See what is the difference. Lambda 2 is 600 nanometer I am writing because this will get cancelled. This is 600. Another one is 800. No, other one is, this is 800 nanometer into m. So this will become directly 3 by 4m. Now see, n is equal to 3 by 4m. Can we have the fringes in half in decimal? No, definitely not. Can you say 1.5 fringes formed? No, 1 or 2 or 3 like this fringes are formed. You can never say 1.5 fringes formed or 3.5 fringes formed. Definitely not. So it means this n is supposed to be such a number that this m is supposed to be such a number that n is a full number. You cannot coincide with any decimal or any other value like this. So let's see. If you take the value of m as 1, so what will n be? If you take the value of m as 1, see, n will become 3 by 4, right? If you take the value of m as 2, so n will become what? 3 by 4 into 2, that will become 3 by 2. Still, this is in fraction. If you take m as 3, that will become 3 by 4 into 3, that will give you 9 by 4. 9 by 4, 3 by 2, 3 by 2, 1, 2, 3. 3 options we have obtained. If you take m as 4, now see what will you obtain? That will directly become n is equal to 3. So it means you have to choose the such a number that you do not get the fraction left. You get a proper complete whole number that is left. So here, if we take m4, n will be equal to 3 by 4 into 4. That will give you 3. If n is equal to 3 and m is equal to 4, we have all the values. It means this is saying what? fourth bright fringe of lambda 2 will coincide with third fringe of lambda 1. I'll write down this statement. If you take 8, yes, you get a whole number, but you have to take the minimum value, no? Because in the question, this is saying it is saying calculate the least distance. So for the least distance, we have to choose the minimum value. That's why we are not taking any value. Okay, so for the least distance, since this is written. So this m is equal to 4, n is equal to 3 simply means that fourth bright fringe of wavelength second will coincide with wavelength 2. Now you have mn, take anything. M was for lambda 2 and n was for lambda 1. So if you want to find out y1, that is from n, yn, you can write 3 lambda 1 capital D by small d and solve it. Otherwise, you can use m also, that is 4 into lambda 2 capital D by small d. From any of these formula, you'll get the same result. Fine, this you all can do. See, check whatever answers you're getting. Note this question down. Let me know any difficulties you have, any queries. Copy it.
Sir, how by the way M is 4?
See, we have to choose a minimum value, right? So if you take any value, let's start from 0, right? So definitely 0 means central maxima. So central maxima, we are not considering, we have to find a linear separation. If you take m as 1, you get n as 3/4. So this is incorrect. We cannot have the fringes in fractions or decimals. If we take m as 2, then also you are getting 3/2. This is incorrect. If you choose m as 3, then also you are getting it as 9/4. This is also, as soon as you choose m as 4, you get n as 3. This shows you that this is the minimum value. Understood?
Yes, sir.
See, this is one question given that says that a figure is given. This figure is a part of question only. All these things that are mentioned. So this is the source. From the source here. This is the source. From the source, the waves are going. From the source, the waves are moving here. Fine. Now what will happen? It is asking us that SS2 minus SS1 is lambda by 4. SS2, fine, this SS2 minus SS1 is lambda by 4. You have to find out the condition for constructive destructive interference, obtain the expression for the fringe width. You have to locate the position of the central fringe as well. So see, for these types of question, let us actually know what is the path difference or what is the separation from the linear separation from the central maximum. At least let us obtain the path difference. No, how will we be able to locate for constructive or destructive interference without knowing the path difference? So path difference between waves that are reaching from point P from S through S1 and S2. So see, path difference X will be what? This will be C. If I combine this SS2 plus S2P, see this SS2 plus S2P, this is 1, and SS1 plus S1P, that gives you the second wave. So path difference is what? Path difference is the difference. S2P minus S1P, usually we take this, but right now we have additional component. From here only we have the waves value. So it means this entire minus this entire will give us the path difference. So SS2, this SS2 plus S2P. This is one wave's path minus S1S plus S1P, that is second wave's path. This is what is required. Now let us just solve this. So SS2 plus minus SS1. So When we'll open up the brackets, this will become minus. Path difference from the, no, it's not necessary that path difference starts from the slit only. Usually path difference starts from the slit, which we take S2P minus S1P. But since additional waves are provided, all right, from the source, that's why we have added this component to each. So SS2 minus S1P plus S2P minus S1P. Now see, path 1 of the path difference is already given. That is lambda by 4 was given, not for this extra path. Lambda by 4 was already given in the question. This SS2 minus SS1 is already given as lambda by 4 in the question. It's a part of question only. So what can I write X as? Now what will be the X? X will be, and also one more thing, S2P minus S1P is what? This is the path difference, no? Yn small d by capital D. This also we have discussed. This is the path difference. And this is the additional term is there. If you combine, it simply means Yn small d by capital D was the path difference, right? This we have studied. Additionally, you have this in this question. That is the modification in this question. Otherwise, this would have been the same old derivation. Yn linear separation from the central maximum. Remember, central maximum was this. Then nth separation from the central maximum. We used to write it as Yn. Same thing. Just look into your notes. Turn your pages back. You will see you have done that. Okay. So see, let's solve this. So that makes, let's bring here. That makes this x minus lambda by 4 is equal to Yn small d by capital D. So here we get Yn's value as capital D by small d, and this term x minus lambda by 4, this is Yn. Now this was what was required. Now we can state the conditions of constructive and destructive interference and solve all the questions. See, for constructive interference, x is equal to n lambda. Put it here, put this as n lambda, d by small d. Here, put it as n lambda, lambda by 4. Now you have something, no, where you can put in actually the values equal to Yn. So Yn will become lambda capital D by small d. I'm taking lambda common. So n minus 1 by 4 is left. So this is what, this is the answer of the constructive interference. Similarly, if you take destructive interference, in the question destructive interference was also given, no? If you talk about destructive interference, so see, x becomes, in case of destructive interference, x becomes equal to 2n minus 1 lambda by 2. So put it here in the formula instead of x that we have obtained, because now we can put it. So this becomes d by small d. Instead of x, I will write 2n minus 1 lambda by 4 minus lambda by 4. Why this 4? Because 2 was already there in the question. So 2 into 2 made it 4. This is equal to Yn. So Yn will become equal to capital D by small d, 2n lambda by 4 minus lambda by 4 minus lambda by 4. I've just opened up the brackets. These ones. This is equal to Yn. So ultimately your Yn that will be obtained, this Yn will be equal to lambda capital D by small d, again take it as common. So n minus 3 by 4, no? Just check it once. This is for destructive interference. Fine. This is for destructive interference. Now similarly, in the second part it was saying fringe width, no? Now you can even calculate fringe width. Why? Fringe width was what? The difference between the consecutive fringes. Right. So for any fringe width, you can take Yn minus 1. See, it's exactly like the derivation we have done. Same thing, the way we have studied the derivation, entire derivation that we have done. It's just that this lambda by 4 is extra because now you're not considering your waves from the slit. Your waves have originated from the source and they are there. They have started superimposing there only. That's why we are having difficulties here. So yn is what? Lambda capital D by small d, n minus 1 by 4. This we had calculated also right now. And for n minus 1, same thing we'll put. Instead of this n, we'll write n minus 1 minus 1 by 4. Understood? Instead of this, here we had this n for yn. For yn minus 1, simply put n minus 1 instead of this n. So this will become equal to what? This will also come out to be lambda capital D by D only, no? See, capital D by small d, this will become n minus 1 by 4 minus 1. This, if you multiply, I have taken this lambda capital D by small d common. From here you're left with plus 1, and this will become plus 1 by 4. Yes, class, see, this gets cancelled, this gets cancelled, 1 into lambda d by d, because beta will always be lambda d by d. I have told you earlier also, we have said. Last part was also there, no? One more part was there. What was the last part? It said that locate position of central fringe. Locate the position of central fringe. See, for central fringe, just to do one thing, whenever you are asked to calculate for the central bright fringe, no? For the central bright fringe, whenever you are asked to calculate this, it means n is 0. By n was the separation, no? So for the central bright fringe, this y was always 0. So n will be equal to 0. So in the formula, n minus 1 by 4 lambda capital D by small d, we have to put n as 0. So by n will become what? This will become minus lambda d by d 4 by small d. Take the mod only because there is no significance of this negative sign as such. So take lambda capital D by 4 small d. This will be the answer. Fine, because this was the condition of central place. This is, see, every part that we have done, this is just the derivation only that I have actually written if you match with your notes. It's just that since this S1, S and S2, these were extra which were given as lambda by 4. That's why we were having difficulty, since this is given as lambda by 4, this part. That's why, since this is already given as lambda by 4. Here for SS1 and SS2 were extra. That's why we had to consider this. All right. Note down the question, note down the solution. Wherever you're not able to understand, let me know. Then afterwards, we'll start freshly from diffraction. I hope, Afra, then you'll be able to understand with diffraction then.
Yes, ma'am.
Final answer for destructive interference. See, 2n minus 1 lambda by 4 was there. So I had opened up the bracket. So this became lambda into 2n minus 1. This minus lambda, right? So 2n minus 2n lambda by 4 minus lambda by 4 minus this lambda by 4. Understood? Lambda multiplied by 2n. So that gave 2n lambda by 4 minus lambda by 4, which was left, and then minus lambda by 4. So from here, I have taken lambda capital D by small d common. So what is left? C, 1 minus 1 minus 1. So minus 3 by 4 will be left from here. Understood? I have taken lambda capital D by small d was already there. Lambda also common. So from here, what is left? This n is left. 2n minus 1 minus 1 we get. See, from here we get, if we take lambda capital D by small d common, we are left with 2n minus 1 by 4. Right, so we get 2n minus 2 by 4. So this if I write separately, so that becomes n by 2 minus half. So n minus 1 by 2. Okay, yes, this you were referring to, Sana. Yes, yes. This one, wait. N minus 3 by 4 will not come then, no? Just check, cross-check someone else as well. Because from here, 2n is left, right? Lambda is taken common. Or even if we take 4 common. Yes, yes. Yes, yes, am I right? So if we take, you were confused that it will come or not. Okay, no, lambda I have taken common. 4 also you can take common if you want. From 4 also if we take common, because 4 is also common. Lambda by 4 if we take common. So what will we be left with? 2n will be there right from here. Minus 1 minus 1. So 2n minus 2 will be there. 2n minus 2. Okay, class, let's start with diffraction. All right. See, diffraction is what? Diffraction is basically the phenomena of bending of light. Let me tell you. See, look at the definition later on. Just see what is meant by this. Then you can have a look. There's a screen over here. Right? This is a screen that is there. I have an opaque object kept here. Fine. Now, light rays are falling. All right, this is a block. Let's say this is some block. Now, what is happening? Light rays are coming. But now what will happen? From here, when the light rays are at this point, what will happen? The light rays will touch the screen. Fine, the light rays will touch the screen. As soon as the light ray will come here, it won't be able to move here. As soon as the light ray will come here, it won't be able to move. It will come here. It won't be able to go here. Only this part will allow the light rays to come, no? But see, when the light ray, no, one of the light rays, when it will strike the corner, it should have happened that the light ray just stops over here. But in reality, it was observed through the experiments that there is a bending that occurs over here, like this. Like this, the light rays that touch the screen, like this they appear. So at this part, at this point where the light rays are there, at this particular point, you obtain shadow. The gray, the dark colored part, which we commonly in our language call it as shadow. It should stop there because this is an opaque object. This I have taken as an opaque object, not a glass. If it would have been a glass, then this would have been the case of glass slab, simple refraction through glass slab. But this is not the case, right? So the glass slab I'm not talking, no. That's why this should have stopped, because this is a complete opaque object that I've taken. All right. Now, around at the corner, exactly at the corner, the light rays will bend and they'll spread. And this part you'll obtain will be known as shadow. So see, now see what is the definition of diffraction. Diffraction says that the phenomena of bending of light around the corners, see, around the corners of small obstacles or apertures, you can simply say opaque objects. And then what happens? And its consequent spreading into the regions of geometrical shadow. Why we obtain shadow over here? Because till this particular point, you are able to obtain the light rays on the screen. But because here the corners are not present, so here you do not obtain the shadow. So this phenomena is known as the diffraction. Also, one more thing, class. Remember this, that the size of aperture, this should be less than the wavelength. The aperture that you take, this aperture. So size of aperture should be this aperture that you take for this object. So this aperture should be less than, or at least comparable, like 10 to the power minus 4. So wavelength should be 10 to the power minus 5. Such way, it should be comparable. Less than the wavelength of this light. This wavelength is there and this aperture is there. So both should be comparable, or at least the size of aperture should be less. It should be less than or equal to the wavelength. Now there are two types of diffractions that are present. One is known as Fresnel, other one is known as Fraunhofer. Let me show. So two types of diffraction are present. One is Fresnel diffraction, other one is Fraunhofer's diffraction. Now, Fresnel diffraction, no, this is obtained when you take all the separation. The source is there, a slit is there, screen is there, and these distances you are able to calculate. Yes, this is 5 meters. Yes, this is 4 meters. These you are able to calculate. So that type is known as Fresnel. In case of Fraunhofer's diffraction, no, these are so much at a separation from infinity that ultimately you obtain plane wavefronts. Remember in the starting of the lesson of wave optics, we had done Heinz principle, where we had seen the types of wavefronts that were obtained: cylindrical wavefront, spherical wavefront. So wavefront, because the point source is located at infinity. This is the source located at infinity. So the example that you can take, or not the example, the kind of wavefront that is formed, the type of wavefront that is formed is wavefront is plane wavefront is obtained. Fine. Now you have single slit diffraction, and we'll be studying Fraunhofer's diffraction only. Fresnel's diffraction is not there in your course. Fresnel's distance, this has been deleted. So we'll be emphasizing on Fraunhofer's diffraction. Proper diffraction we'll see. Before that, just note down these introductory points. Then we'll start with diffraction for a single slit. No, you don't need to learn about them in detail. Fraunhofer's diffraction, we'll see. So that the whole condition of maxima, minima, all these things will be included. But Fresnel, you don't have to even remember the name. That is not included in your syllabus. Now diffraction at a single slit. So single slit diffraction, let us study. For this now we require lens because we need to bend the objects. See, this is a source. Here I have taken a single large slit. Fine, this is single slit diffraction, which is known as, this is the Fraunhofer's one. Now, why am I taking a convex lens? The need is that because now the source will get diverged. From the source, no waves will keep on moving. But now we have to obtain it at a certain point. This is a targeted point. So even though if the source is generating waves like this will do what? This will perform the work of refraction. Like this, refraction will occur. Now refraction will occur. Now what will happen? Let's take here also we require a larger lens. This was done actually experimentally by Fraunhofer. The way we had Young's double slit experiment. He did whatever he liked. Young's double slit experiment. Same thing you have in case of this. The way we had Young's double slit experiment. Same thing. This is Fraunhofer's experiment. But this will come to you in the exam as simply single slit. Yes, diffraction takes place from the corners only. This was just an experiment done. This is not the daily life diffraction examples that we are taking. This is a proper experiment that was conducted. So see, if this ray of light strikes here, this ray of light, one ray of light from here, this will strike over here. And one ray of light, this will come from here. Again, this lens will do what? This lens will again refract it, and this will obtain the central maxima. That's why we did this. Here we'll obtain the central maxima. Fine. This is just the source slit. Let's say A is the slit width. Fine. This point, let's name this point C. This point as D. Now C. From these points, this is the corner. This is a plane wavefront. From here, the diffraction will occur now from this end and this end. This is what we have studied. Diffraction is now supposed to occur. So here it will get, the light ray will bend. And here the light ray will bend from the original path. This I'm just trying, or delete it. Now see, here we'll obtain the image. So this part, this is the point P, and this becomes Yn in case of diffraction. This is the screen that is obtained. Now for the derivation, I am dropping a perpendicular. Let's say this point is N. This is a perpendicular point that I have drawn for this. So see, let's take this angle as theta, and this will also become theta. Any of the angles that you will choose, any of these angles, this will become theta n only. Fine. And also one more thing, here you will obtain a plane wavefront, which we have discussed. No need to mention it. If you want, you can mention it. And what is this now? This is actually the focus of the lens only. Then only the light rays are becoming parallel. So this is actually the focus of the lens. This also you should keep in mind. Then only you obtain all these points. Now derivation in triangle ADN CD. In this triangle CDN, this triangle CDN. If you look at this triangle, see this is theta n, right? Just look at this triangle. This is theta n, this is C point, this is N point, this is D point, this triangle. This was the perpendicular though. So here sine theta n, this will become dn, the perpendicular, by hypotenuse, that is CD. dn by CD. So dn is what? See, dn is this some unknown dn, we do not know. So let's keep it as dn only. CD is small a. So dn by a. So from here we have the value of dn. Understood? From here, we have the value of dn. dn by CD, yes. So from here, we have the value of dn. dn will become a sine theta n. This is the path difference that has been obtained. All right. Now, if you take the small angle approximation, if you take tan theta from here, if you take tan theta from here in this triangle, so see tan theta n will become what? Perpendicular by the base, right? So that will become yn divided by capital T. See, how did we take this one? Look in the figure. This big triangle I'm talking about, this triangle, this bigger triangle, this is also theta n, this is yn, right? And this is the base. This also you can write it. So tan theta is yn by capital T, or you can do even one thing, you can directly write yn as theta n into T. Now, conditions for the secondary maxima. Secondary minima. First, we have the minima. See, path difference is what? Path difference is n lambda. So, a sine theta n that we have obtained here. A sine theta n. So, what will this become? This will be equal to n lambda. So, sine theta n now is equal to n lambda by a. So use small approximation. What do we obtain? We obtain theta n as n lambda by a. N lambda by a. This is what we have obtained. Theta n lambda by a. That is sine theta n almost equal to theta n, that is n lambda by a. So this is what we have obtained as the angular separation. So this is the angular separation. And what about the linear separation? Linear separation will be theta n into capital D. This is written in the which manner? This is just by arc of length. Theta is the angle. This is capital D. This you have as capital D, separation base. C class. This base you have as capital D. This is yn. So from tan theta only this is calculated. And for here, minima, conditions of minima, you have n lambda by a. So this becomes n lambda by a into capital D. Now see, you can use any, you can use small angle approximation is valid here. See, what did we do right now? Let me repeat it. Using this triangle, CDN, a sine theta was calculated. A sine theta came out to be yn. Now yn is, path difference is n lambda for minima. So see, for minima, what did we do? We had written the conditions for minima. So n lambda was equal to the path difference for minima. So a sine theta becomes equal to n lambda. Right, from here we get the value of theta n, that is the angular separation, right? And yn, if you look at this triangle, from here tan theta n is equal to yn by capital D. From there we get this again, tan theta n will almost be equal to theta n, so we write this. And here from theta n's value we keep it, so we get n lambda by a. Similarly, for if you have maxima, secondary maxima if you choose, what is the difference? Path difference, there will be just a difference in the path difference. That is 2n plus 1 lambda by 2. Where your n is 1, 2, 3 onwards. So see, now your a sine theta n will be what? Instead of n lambda was for minima. Now this will become 2n plus 1 lambda by 2 for maxima. Understood? Even if you want to write sine theta n will become 2n plus 1 lambda by 2a. So sine theta, if you write, you choose small angle approximation, theta n will be equal to lambda by 2a. And again, if you want to write, if you wish to write the linear separation, so see, same thing. linears for the linear separation, that is yn. This will be equal to theta n into d. So yn will be equal to 2n plus 1 lambda by 2a. Just multiply it with capital T. This becomes the linear separation. First, tell me, is it clear? This is just similar to the first one. First, understand this minima one. If you have understood the minima one, secondary one is not different. It's just the value of path difference. First, tell me, any doubts still here? Do you want me to repeat any part? This derivation can also come. Yes, class. Clear to all of you?
Yes, teacher, clear.
Okay, if it's clear, then please note it down. From diffraction, from here only, you have to write rest of the things you have obtained. Then we'll do numericals based on this. This derivation can be asked to you in the exam, though from this part, now your CBSE board exams, directly you get numericals more. More you have numericals than the derivation part. But yes, definitely you can get numericals as well. The derivation as well. Numericals will be there. I'll show you how what type of numericals come from. All right, this question says what? A parallel beam of light of 600 nanometer. This falls on a narrow slit and resulting diffraction pattern. So what is the wavelength? The wavelength is lambda is 600 nanometer. That is 600 into 10 to the power minus 9 meter. Resulting in diffraction pattern, this is observed on a screen 1.2 meters away. Capital D is 1.2 meters. It is observed that first minimum is at a distance of 3 millimeter from center of screen. Separation from center of screen, separation from central maximum, linear separation from central maximum. This is Y1 that is given 3 millimeters. That is 3 into 10 to the power minus 3 meters. And what else? Calculate slit width. A is missing. So it's not difficult now. Y1 is equal to lambda capital D by A. Right. So A will be equal to lambda capital D by Y1. So what will be the answer, class? This will be 600 into 10 to the power minus 9 into 1.2 by 3 into 10 to the power minus 3. So 2.4, right? 2.4 into 10 to the power minus 4 meters. Just check the calculations once again and note down the solution. See class, this question says that in a single slit experiment, light of wavelength 6000 angstrom is used. Slit width is what? 2 millimeters. Separation from screen is 2 meters. So small, this is small d, this is capital D, and lambda is given. Now see what you are asked to calculate. Separation of first secondary maxima from central maxima, both linear and angular. So n is equal to 1. Like this only you will get questions from wave optics. These won't be so difficult. That's why I'm saying derivation. If you have not understood, let me know. Questions you all will be able to manage, and questions do come. See, this is n by a angular 1. So n is 1 for the first part. So theta 1, this becomes lambda by a. Lambda is 6000 angstrom. So 6000 into 10 to the power minus 10. This was given what? 2 millimeters. So 2 into 10 to the power minus 3. So 3000, 3 into 10 to the power minus 4 radian. This is angular one. It is written both angular and linear. So y1 is equal to theta 1 into capital D. We did, right? We did this. So this will be equal to what? Y1 will be equal to 3 into 10 to the power minus 4. Separation was what? 2 meters, right? 2 meters. This becomes 6 into 10 to the power minus 4 meters. Same thing. Now, second part says what? Separation of secondary maxima. This was minima, no? Here we had to calculate minima. So we use this formula. Now you have to find out maxima. So theta n will be 2n plus 1 lambda by 2a. And n is 2. N is not 1. This is the difference because this is maxima now. This is the difference that will arise. So theta 2 will be 2 into 2 plus 1 into lambda by 2a. That gives you 4 plus 1, 5, 5 lambda by 2. So theta 2 will be 5 into wavelength was 6000 into 10 to the power minus 10 by 2 into a was what? 2 millimeters. So 2 into 10 to the power minus 3. So this will be 4. Here you have 3. So 7.5 into 10 to the power minus 4 radian. Do check the calculations whenever you're writing. Sometimes while writing, the calculation error can be there. Just check when you're writing. And same thing, y2 will be equal to theta 2 into capital D. So it means 7.5 into 10 to the power minus 4 into capital D was what? 2. So this becomes 15 into 10 to the power minus 4 meters. So both angular and D. Fine, note down the question. Any doubts you have, let me know. Okay, one last numerical. A parallel beam of light of wavelength 600 nanometer. This is incident normally on a slit of width A. This we have to calculate this width. So if distance between slit and screen is 0.8 meters, it means this is capital D given, slit and screen distance. And the distance of second order maximum, N is 2, maxima is given, 15 millimeter is small d. See, this is not difficult. Again, once again, these types of questions only you have. For maxima, we use this formula 2n plus 1 lambda by capital D divided by 2a. See, n is given as 2. Lambda is 600 into 10 to the power minus 9 meter. Capital D 0.8 meters. N is 2n. Anything else? लिख दिया ना? N is 2 lambda capital T. All right. Here we have to find out y2, right? So this will give us y2. So y2 will come out to be 15 millimeters. This is given. And the distance of second order maximum from center is 15 millimeters. So it means this is central one and this is the y2. So this separation is the linear separation, that is 15 millimeters or 15 into 10 to the power minus 3 meters. Now let's keep everything into the formula. So y2 will become equal to 2 into 2, 4. Again, 5 lambda capital D by 2a. A will be equal to 5 lambda capital D by 2 y2. So A will be 5 into 600 into 10 to the power minus 4, right? Capital D is 0.8 divided by 2 into 15 into 10 to the power minus 3. Just check what answers you're getting. 2 is there, this 15, so 3, then 6 gets cancelled. So that will be 0.8 only. 0.8 into 10 to the power minus 7 meters, right? 0.8 and this 10 to the minus 7, rest things will get cancelled. When you're writing, just check the calculations once again. Let me know if there is any error. Okay, note it down. Okay, C class. So I think last topic for today, let us just calculate width of central maximum. See, width of central maximum means if this is this source and from the source, this is the slit and the slit, you're able to observe two angles. Two angles in the sense, one angle that has been formed above the central maxima, one below the central maxima. So we call both as the minima only, no? The way we had bright fringes on both the sides and dark fringes on both the sides, we obtained a angular width also there in the case of interference. Same way here also, this entire angle that is subtended. So this entire angle will become what? 2 theta 1. If this is theta 1, this is theta 2, both theta are definitely equal. So this will become 2 lambda by a. Because theta was lambda by a, so this will become 2 lambda by a. And even if you want to find out linear width of central maxima, so that will be angular width multiplied by capital D. So directly you will get linear width as 2 lambda by a. This will also be used in numerical zone. Okay, noted. I had already announced the test so that I will take this week for Wednesday. So diffraction I will not include because diffraction you have done today only. So how will you be able to revise it within just 2 days? Do one thing, let's take the test. Let's just have the test of interference. So I think just interference will be fine by all of you. Okay, fine by Salman and others. Memuna, Khalid, Sana. Wednesday, half an hour test is fine.
Okay, teacher.
All right. Then interference, I'll take the test on interference. Then Heinz principle and this diffraction, I'll take. You have an exam on Thursday, Sana. So you will attend the class or not? Okay. Fine then. Then let's see on Wednesday then. But I'll take the test this Wednesday. Because for Heinz principle and diffraction, I'll take it together then. You can then submit me as an assignment, Sana. And I hope Memuna will be appearing for this time. Last time you had promised Memuna. So as you all will complete, you all can leave. I think this is enough for today. Lots of topic for diffraction we have covered. Half an hour more class is required that I'll complete on Wednesday. Then this lesson is over and I'll start with model physics. So wave optics is almost over. Just intensity distribution curve is left. That also could be completed in 5 minutes, but let's just stop. Otherwise, it will be difficult for all of you. Intensity distribution curve for this is left, diffraction. And 1 to theory questions at least I'll discuss with you. I'll write down the theory portion before the class so that time will be saved and we could move on to modern physics. All right, then. So those who will complete, you all just text me done. You all can leave.